All right. Section 3 for exponential and logarithmic functions. Okay, so short and sweet here. This one is just about applying the one-to-one property of exponential and logarithmic functions to solve equations. So now we're looking at, we've already used the properties to evaluate them. Now what we're doing is looking at solving the equations. Kind of a pattern, right? We look at graphs, then we look at evaluating expressions, and then we get into equations with each chapter and how to solve them. So a couple things here to write down and look at is that in words here, if you've got b is greater than 0 and not equal to 1, then this property applies. If you've got b to the x power equals b to the y, if and only if x is equal to y. We kind of saw something similar to that in section 3.2, where you have the same base. That means that their exponents are equal. And we were solving for the variable there. So another way to put that as an example is if you have a base of 3 to the x equals 3 to the 5, then we know that x has to equal 5. The exponents are equal. In logarithmic form, we could say that if we had log of x equals 3, then we could say that 10 to the log of x would equal 10 to 3. Why that is because, remember, if we don't have a number written here, then it's considered the common logarithm and makes it 10. So now we take this as our base here, and then we take this part here, put it as the exponent, and then the base again here to the third power. Okay, so we're kind of going to work back and forth between exponential and logarithmic functions and kind of solve the equations this way. Okay, here's a little example here. We call it exponentiating each side of an equation. Okay, so when we do that, we've got some examples to look at. And like I said, what we do down here is we call this exponentiating side. So when we apply the one-to-one property, that's what we're going to call exponentiate. So notice the effect above here in this example right here when we exponentiate each side. So you have log base 2 of x equals 3. So kind of like we did right up here is you take the base here and raise it to the log power and then to the third power here. And then because you have the same base, 2 and 2, then that means these things are equal. And one way to think of it, remember, is that if you've got, I guess another way to look at it is, remember this is an inverse property of itself right here, 2 log 2. So that would kind of inverse back to 1. So now you're left with this. Okay, so that's kind of the example we'll give you, and then we'll work through a few others. All right, the one-to-one property just tells us, kind of like we were talking about with logs, in this case, b is greater than 0 and not equal to 1, then we can say that the log of b, log base b of x equals log base b of y if and only if x equals y. So very similar to what we saw up here with exponential functions. I was doing that with exponential functions. The same thing can be said logarithmically. Okay, so an example here would be that if we have log 2 of x and log 2 of 6, then we know that x has to equal 6 right here and right here because they have the same base, basically the same log, right? In terms of e with natural logs, if we have e to the y equals 2, then we know that e to the y equals the natural log of 2. Okay, so continuing on, because basically remember that those inverse properties, you got to remember those from the previous sections as well. All right, to solve these, what we're going to do, we're going to try to create common bases. We kind of, like we said, we kind of did that a little bit in 3.2. We're going to try to create common bases, and then with exponentials, so that's the key, again, exponential functions. And when we're doing logarithmic ones, we want to isolate the logarithm, just like we do when we're solving radical equations in the last chapter, right? We wanted to isolate the radical, here we want to isolate the logarithm. Now, I'm also going to give you a packet of textbook examples. I know you have the textbook, but I'm going to give you a copy of a bunch of examples because sometimes when you see the problem, it's just easier to find one that looks like it and then work through that to do the examples. So I'll give you that copy as well, and you'll also have these examples, so you have a whole bunch of examples. All right, first one here. So we're solving this. We've got an exponential. It looks like they're in exponential form. So we want to get to the same base. So that's what we're trying to do, is get common bases here. So I can see that 16 and 4, I could write 16 in terms of 4. So I've got 4 to the x plus 2 power here. And then I can rewrite this 16 squared as 4 squared. I'm going to use parentheses because it's going to be 4 squared to the x minus 3 power. Now, on the left side, I still have 4 to the x plus 2. Over here, remember, I'm going to multiply these right here, the exponents. Power to a power means multiply. So I'm going to go 4. I'm going to distribute. 2 times x equals 2x. 2 times negative 3 equals negative 6. So I have those. Now, because I have the same base here, that basically tells me that my exponents are equal. So I'm going to go x plus 2 equals 2x minus the 6. And then I can solve from there, solve for x. I end up by subtracting 2, subtracting an x, and adding 6 to both sides. I get x equal to 8. All right, let's look over here. Same general idea. Can I write them in terms where they're the same base? Well, I have 1/3 to the n power, and that can stay like that because I noticed that 81 and 3 might have some action in common. The 81 could be a power of 3. So I could keep the left side the same. The right side I'm going to rewrite as 1 to the 3 to the 4th power, because that's what 81 is. Then to the 2/3 power here. Now, a little bit tricky stuff, because remember we have fractions. We can flip them over and make it a negative exponent, right? So I could say that this would be 3 to the negative n power, and then over here I would have 3 to the negative 4 power to the 2/3 power. Now I have to basically say I have the same base, but again I have to do a power to a power here, so I kind of have negative n equals negative 8/3 when I multiply 4 by 2/3. And I have the same base, so I can do that. So that means that n has to equal a positive 8/3. Okay, so pause and rewind as you like. I'm just trying to move through this. A few more examples for us, and then we'll be done. All right, so we have 2 natural log x equals 18. So now we're talking log, so I want to isolate the logarithm if I can. So what I'm going to do is I'm going to just divide by 2 like I would in algebra. So I have natural log x equals 9. Okay, now, since we're dealing with natural logs, we're talking about the base being e. So I can write this in exponential form with e as the base to the natural log x equals e to the 9th power. Now they have the same base, so I can say that, oh, and because they have the inverse right here, this part right here, remember e, one of the properties with e, is e to the natural log x power is just x. So I have x is e to the 9th power, which then I can just do here and say 8103.08 would be my final answer there. Okay, again, just noting that this right here, remember we have that property that if it's e to the natural log x exponent, then it is x, kind of an inverse function of each other. All right, moving over here. Again, same thing. If I can just subtract 7, I want to isolate, that'll give me minus 3 log 10x equals 6. And then if I divide by the negative 3 here, I'm going to get log 10x equals negative 2. Now, what I want to do here is I want to rewrite this in exponential form, but it's key to just point out that, remember, if there's not a log, if there's not a base, then we assume, I should use a different color, that it's log base 10. So in that case, when I rewrite this in exponential form, from log form to exponential form, I'm going to say that it's going to be 10 to the negative 2 power equals 10x, right? So if you think, remember exponential form, what it does, it takes this part here, puts it at the exponent, that takes this part here, puts it on the other side, and then your base goes right here. Now I have 10 to the negative 2 power equals 10x. Now I can try to solve. Now remember, if you can remember that 10 to the negative 2 power is going to be 1 over 10 squared, or 1 over 100, then we're in good shape, equals 10x. And then I'm going to divide by 10 on each side. And by doing so, I'm going to get a decimal, or 1 over 1,000. All right, let's continue. 3 more. We can roll through these pretty quick. You can always rewind and come back. All right, so here, now what I want to do is I can condense this because I've got a subtraction problem. So I can make it I can use the quotient property that we learned in 3.3 and do this. Log base 2 of 5, and I can take this subtraction and make it a division problem. Log base 2, and then I can say, put 10 over x minus 4, because I can take these two things and make them into a quotient. So now I have the same base, the same log, right? Log 2. So we can use the 1-to-1 property because these are the same. And that allows me to say that now just 5 is equal to 10 over x minus 4. Now I'm basically just trying to solve for x. So by doing that, what I'm going to do is I'm going to multiply both sides by x minus 4. That's going to cancel here. I'm going to be left with 10. And over here, I'm going to have 5x minus 20 when I distribute. Add 20 to both sides, 5x equals 30, so x equals 6. All right, 2 more to go. Rolling through problems, and you're going to get a whole bunch more as well. Okay, so now I'm in exponential function. I have 3 to the x equals 7, and so what I want to do here now is I want to make them a common log, take the common log of each side. So if I take this log 3 to the x equals log 7, and it's a common log. Remember, there would be a base 10 here if I wanted to write that. Okay, so I could do that. I don't have to because it's common. All right, now basically I'm going to use the exponent function. It's going to bring this exponent over to the front. So x log 3, the product, the exponent rules, log 7, and now I'm just trying to solve for x. So I'm going to divide by log of 3 on both sides. And now I can use my calculator to say x is log 7 divided by log 3, which is about 1.77. All right, we are rocking. All right, one more. So same thing, another version of these exponentials that we want to take to our log, but here we're dealing with e, so we're going to take the natural log of each side. So if I go ln of e to the 2x plus 1 equals natural log of 8. So now what I'm going to do, again, if I look and see that whatever I have natural log of e and an exponent, remember my answer is just the exponent. It's an inverse function. So this is going to be what's left here, 2x plus 1. Can't do that on the right side, though, so it equals the natural log of 8. And now, again, trying to solve for x. So I'm going to subtract 1 from each side. I'm going to get 2x equals natural log of 8 minus 1, and then I'm going to divide by 2. So x is going to be natural log of 8 minus 1 over 2, or as a decimal, we could say 0.54. Okay, so we rocked that out and finished that up. And I don't know how long it took me. Let's see. 15 minutes. Hey-o. All right. Awesome. Bring your questions to class the next time I see you. Bye-bye.